All right, so in this video, we're going to talk about how we can manipulate some of these Maclaurin series to possibly help us come up with some other ones that will also be helpful. And so in the last video, we spent a little bit of time going through the process of coming up with this specific Maclaurin series. Now, before I move away from it, I do want to point out, I think it'd be good for you guys to read Operations on Power Series, page 616 and 619. I think it's a good couple paragraphs, couple pages to read, but I'm going to show you intuitively how things work the way they do. So we came up with this, understanding where that formula came from for the Maclaurin series itself, but I'm also now going to go ahead and integrate both sides of this. Now, as I integrate cosine, we know that the result is, of course, going to be our sine. And on the right, if I go term by term through this, I'm simply going to add 1 and divide. So the x, or excuse me, the 1 is going to turn into the x. The next one, if you add 1, you get a 3. When you divide by the 3, that's going to be a 3 times 2 factorial, which is just a 3 factorial. So we're going to have our x cubed over 3 factorial plus, and then similarly, add 1 to 5, divide by the 5. 5 times 4 factorial would just be 5 factorial. So that's going to be plus x to the 5th over 5 factorial. And now at this point, you're probably again starting to see that pattern. We'd have a minus x to the 7th over 7 factorial plus, etc., etc., etc. So by knowing cosine, we're able to come up with the expansion for sine. And just like the last video, I showed you how to come up with that summation notation. I would encourage you to note the same thing here. In this case, we're going to have to start at 0 with -1 to the n, because again, just like the last one, starting at 0, that's going to wipe this guy out and make us start with a positive number, followed by an x to the 2n plus 1 over the 2n plus 1 factorial. That's going to give us our even number plus 1, giving us our odd number. So 1, 3, 5, 7, same thing down here. Even though I don't have it written, it can be clearly seen that that would just be a 1 factorial there, following the pattern. And of course, 1 factorial is 1, so you're not really quite seeing it at its face value. All right, so now that you've seen sine and cosine, and those are ones you definitely want to remember. Those are going to come up a lot. There are a few others that are worth mentioning as well. So we've got the x to the n, which again, if you just plug in the number for n, you can see that you'd get a 1 plus x squared plus x cubed plus all the way down to whatever. And that's actually going to be 1 over 1 minus x. And we know this because if we're talking convergence, and this is a power series, in which case we would select x's in which it would cause it to converge, this would converge to that by geometric. So this whole idea of x to the n is more of a geometric representation. So another one that is not necessarily as intuitive, but you could certainly write it out and go out as many terms as you need to evaluate it and convince yourself, would be this x to the n over n factorial. This would be a 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial, etc., etc. This actually comes out to e to the x. Okay, so plug a 1 in for x. If you put a 1 in for x, there, and you add up a bunch of these terms, you'd find out you'd get pretty close to e to the 1st, which would be that 2.7 whatever. So again, I would encourage you to do that to convince yourself. Write out maybe 10 of these terms, replace all the x's with 1s, add them all up, and it should get you very, very close to e to the 1st. The reason why I wanted to bring up that one is because if you know e to the x, then you also know cosh of x and sinh of x. So let me go ahead and clear the screen, and I'll show you how we can come up with those based upon using that e to the x from just a moment ago. Okay, so you can see I've got the e to the x back up on the screen, and let's take a look at cosh of x. So if we want to come up with the Maclaurin expansion for cosh of x, we know that's going to be e to the x plus e to the negative x over 2 which is the same thing as 1/2 times e to the x plus e to the negative x. So now, the e to the x is going to be this guy right here. So I'm just going to take this and drop it in right there. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4th over 4 factorial, and we could go out as far as we need to. And so then I'm going to have a plus, all right, so maybe I'll put some parentheses in here to make this a little more clear. That grouping there is going to be this guy right here, and that plus that you see is going to be this plus right here. So let me go ahead and I'll throw some more parentheses in. Now we're going to have e to the negative x. So e to the negative x is going to be this guy right here, but every place I see an x, I'm going to replace it with a negative x, okay? And in doing so, that's still going to give us a 1, but now we're going to have a minus x plus x squared over 2 factorial, and then a minus x cubed over 3 factorial. So you can start to see now every time we hit an odd power, because when we take a negative x and plug it in, it's going to spit out the negative, and so our term will change signs. And then if I wanted to continue, maybe I'll have a plus x to the 4th over 4 factorial, then I'd have a minus, and go out as far as you need, and close it up. Okay, so now let's combine some stuff. Because these negatives are now part of that second grouping, the x and the negative x are going to go away. The x cubed terms are going to go away. The x to the 5th terms are going to go away, leaving us with just this 1/2 now, times the result we get when we combine all this stuff. So a 1 plus 1 would give us a 2. Then we would have a x squared over 2 factorial, x squared over 2 factorial, so we'd have 2 of those. So 2 times x squared over 2 factorial, and then 2 times x to the 4th over 4 factorial, and you can continue that again as far as you wanted to go. So now when we take this 1/2 and distribute it, those 2's are all going to go away, leaving us with the result of 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, x to the 8th over 8 factorial, all the way through. So there sits the Maclaurin expansion for hyperbolic cosine. And you can see how this relates to the trigonometric unit circle cosine that we've discussed earlier in I believe the previous video as well. Now, we've got cosh. Let's say that we want sinh. Well, we also can use a little bit of calculus. If we take the derivative of cosh of x, then I'm just going to take the derivative of this guy here, term by term all the way through. And so that's going to give us our sinh, which in this case, when we take the derivative, this guy would be a 0. For this one now, we would multiply the 2 down, and maybe I'll write this one out. This one's a little harder to see. So I'll multiply the 2 down, so 0 plus, and subtract 1. And then in the denominator, that's going to be 2 times 1. So 2 factorial is 2 times 1, and you can see those end up going away. Similar for the next one, we would have 4x cubed over a 4 times a 3 factorial, and the 4's would go away. And then at that point, the pattern is pretty clear. So maybe I'll write this out as x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial, as far as you needed it to go. And I would also note real quick that you can see how this relates to your sine expansion we saw in the previous video as well. They're very much related. You can see that. I don't want to go into a ton of detail in talking about it because I don't have it up on the screen to relate it, but you can check your notes and see how that all ties together. It's really, really interesting how all of this comes about.